Alright, welcome to lesson 3-1. 3-1 is all about constant rate of change, which you are very familiar with from last year. In example number 1, they're asking you to determine whether or not the relationship in the problem is a linear relationship, and if so, then you need to find the rate of change. And the way we determine whether or not the relationship is linear is to check for a constant rate of change. If the rate of change throughout the entire problem remains the same, then we have a linear function. Okay? So in this problem we have a number of transactions on the left and dollars on the right. So we go through and we check the rate of change for each individual one. In this case it's rising by 3 in each cell. And then over here for dollars it is decreasing by 30 from cell to cell, and it's constant throughout. So we can look at our rate of change, and remember it's always this column, negative 30. This would be the y column. Y over x is negative 30 over 3, and that would be negative 10 over 1. We can just call it negative 10, and that means that it's $10, and it's a withdrawal of $10 each week, as opposed to putting $10 into the account each week. It's a negative relationship. It is indeed linear because it has a constant rate of change. Please do letters A through B. Example number 2. Don't forget, first of all, to put the key concept on page 173 in your notes. It should probably go on your gold sheet right from the start. Okay, in this table we're doing the same thing. We have Celsius degrees on top and Fahrenheit degrees on the bottom. And I didn't put each individual one, but I checked them all, and they are all plus 5 for that column, and for this one it is all plus 9. So again we have, this is the x and this is the y. This is input and output, we could call it. So it's the y 9 over the x 5, so it's 9 over 5 degrees Fahrenheit to degrees Celsius. So we put that it is indeed linear, but it is not proportional. Now the way they show that it is not proportional in the book is that we have 41 over 5 and 50 over 10. We could do the math here, but it's plain to see that this is 5 and this is clearly not 5. This would have to be 25 on the top to come out to be 5. So we do not have a proportional relationship. But I'm quite sure that you were all taught last year with Mrs. Shaw that if it does not go through the origin, immediately you can determine that it is not a proportional relationship. Since it does not go through the origin, I don't think you even need to do this calculation. Please press pause and do letter C. Okay, here are your solutions to your letter problems for 3-1. Again, we're being asked, is this a linear equation? Or, I'm sorry, is this a linear relationship? And if so, what is the rate of change? So we have minutes on the left and degrees Fahrenheit on the right. We move through here and we see that we are adding 5 in each case. Do the first one and we see that we subtracted 5, and then the next one we would have to subtract 4. So immediately we can stop. We don't even have to go to the next data cell. We can say that it is not linear because it is not a constant rate of change. Letter B. In this case we have 3 plotted points on the chart, and you can see that we have minutes on the vertical axis and volunteers on the horizontal axis. And basically we look at this and we can see that we drop 20 and add 8. Drop 20 and add 8 in each case. So we can say yes, it is a linear function. We have a constant rate of change. It's negative 20 over 8. Okay? And that reduces to negative 2.5 minutes per volunteer. Remember, always turn it to a unit rate. And letter C. Again, we're being asked if it's linear, but then also we're being asked to find out if it is proportional. So the first thing we do is check the differences in the x value, and it's rising by 20 from cell to cell, and the y value is rising by 9 from cell to cell. We have pounds versus kilograms. So our rate of change is 9. Remember, always do the bottom one here, the y-axis, 9 over 20, the x-axis. We can also say that it is proportional because if we went backwards and we subtracted 9, we would get to 0, and if we went backwards and subtracted 20, we would get to 0. So we know that it goes through the origin, or 0, 0, and therefore it's proportional. Additionally, we could take 20 divided by 9, 40 divided by 18, and you would keep getting the same ratio there. It is a proportional relationship. Please complete your guided practice. Here are your solutions to 3-1 guided practice. Our first problem, we have a number of chairs and we have a number of cans of paint needed to paint that many chairs. So we are being asked whether or not this is a linear relationship. So we look at the left side, the x values, and we see that we're rising by 5 from cell to cell. And in the y values, we're rising by 6 from cell to cell. So the change in y over the change in x is 6 over 5. So we have a constant rate of change because these are the same, and therefore a linear relationship. So yes, it's linear, and our rate of change is 6/5 of a can per chair, or you could write it this way. I would say that this is probably better, especially when we get to the next lesson, we start talking about slope. You'll see that this is kind of advantageous. So this is probably the best answer, but they're both correct. Problem number 2. We have feet graphed on the vertical axis and minutes graphed on the horizontal axis. And we have points here, here, and here. Now these points here are not real easy to determine the rate of change, so I chose these here because we can see that this one is clearly on the 3,000 mark, and it drops from 3,000 down to 2,000, or in other words 1K. You should all understand what K stands for. It's 1,000. So it drops 1,000 from here to here, and our horizontal run is from 2 to 6, so it's a +4 here. So it falls 1,000 feet in 4 minutes. As you can see, it falls 1,000 feet in 4 minutes from here to here. And we can get that into a unit rate of -250 feet per minute. So we do have a linear relationship. Another way to recognize a linear relationship is to determine whether or not the data points are in a straight line. So if you were to put a ruler on this in your book and see that they all line up perfectly in a straight line, we can say that that is a linear relationship based on that. Problem number 3. We're being asked if problem number 1 was a proportional relationship. And our answer is yes, because the ratios are constant, and also because it goes through the origin. So we look at it and we ask, is it proportional? We could say that 6 over 5 is the same as 12 over 10 is the same as 18 over 15. That's one way we could do it. Or another way we could do it is go like this and say that we're going backwards, so it's -6, we would have 0 here, and we're going backwards, so it would be subtracting 5 here, and we had bet 0. So indeed we would go through the origin, and going through the origin shows that a relationship is proportional. So either way, you could look at the ratios and show that the ratio is 6 over 5 in any case, or you could look at the origin. And of course our rate of change again was 6/5 of a can per chair. Problem number 4. The answer to that question is we can compare ratios, which is what we just talked about doing, or we could solve for the values at the origin. If the relationship goes through 0, 0, it is proportional. So that's 2 different ways that we could look for proportional relationship. Look at the ratios and make sure they're constant throughout, or if it goes through the origin. Please do independent practice.